Hello, I'm Yulia Svetashova. I am a PhD candidate at Robert Bosch Corporate Research. I am presenting joint work of Baifan Zhou, Tim Pyshinsky, Stefan Schmidt, Jörg Sureveta, Ralph Pikut, Evgeny Harlamov, and mine. Our paper introduces a Bosch use case of quality monitoring in welding. Welding is a fully automated process, heavily used for numerous applications in car production at Bosch factories and by many Bosch customers like Daimler, BMW, Volkswagen, and others. During welding machines connect pieces of metal together by pressing them and passing high current electricity through them. A typical car body can contain up to 6,000 welding spots. Each spot generates thousands of sensor measurements. It typically results in millions of data records for only one car. The quality failure of a single spot can halt an entire car production line and thus lead to delays and costly repairs. To address that, Bosch is developing machine learning methods which predict the quality of next spots before the actual welding happens. The journey from data to a machine learning model takes a lot of time. The workflow of machine learning development starts with data collection and task understanding. This step is followed by data integration to prepare the inputs for the two model development steps, feature processing and machine learning modeling. Finally, data scientists interpret the results and select the best model. This workflow is a complex and costly process. There are three challenges that take more than 80% of the overall development time. The first challenge is communication. Task understanding requires collaborative work of experts from different areas, including data scientists, engineers, process experts, and managers that have asymmetric knowledge background. It makes their communication time-consuming and error-prone. The second challenge is data integration. We integrate data from dozens of sources with lots of manual modification. The third challenge is the generalization of machine learning quality models. Each developed machine learning model is typically tailored to a specific dataset and one welding process, and the reuse of this model for other data or process requires a significant effort. We address these three challenges by enhancing machine learning development with semantics. Our solution is implemented as a system, we call it SemML, and next I will explain the core ideas behind it. One of the main components of our system is the core ontology for manufacturing. It describes manufacturing in a very generic manner. It has axioms that link its entities to the machine learning ontology classes. There, they are defined as machine learning feature types, time series, categorical variables, identifiers. And finally, there is a machine learning pipeline catalog with the instances of concrete pipelines described in terms of machine learning ontology. Our backend can execute these pipelines automatically, taking as input annotated datasets. If we had only one process to deal with, we could use the core ontology for manufacturing for integration. But even welding has multiple types and variations. To address this challenge, we provide tooling and templates to construct ontologies for other processes. With that, whether it is the ontology for resistant spot welding, or hot stacking, or ultrasonic metal welding, or packaging, it will be fully compatible with the automated machine learning workflow. I'll now introduce this core ontology for manufacturing. It's an L2 ontology, and it models the processes of discrete manufacturing with emphasis on quality analysis. It takes operation-centered perspective because we model the quality of a single operation. An operation is performed by a machine on a raw resource, and it results in an operation product. The resource can be an assembly and have components. Machines, machine parts, assembly components are uniformly described as physical entities having their geometry, material, and surface conditions. Software systems that control a process contain several functional modules. We can record settings and status parameters for them, as well as programs. Programs set reference values for quality monitoring, and these values are compared with properties of the products. Some of them become quality indicators. Finally, during the operation, we collect sensor observations and store them as operation curves. This model is very generic, and its components can serve as templates to describe concrete manufacturing processes. I will now show how one of such templates works for resistance spot welding. The product of a resistance spot welding operation is a welding nugget. The nugget has a property named nugget diameter, which is an important quality indicator. To construct a class for a welding nugget diameter, a user will select a template operation product property in a graphical user interface, give property a name, select a more general physical quantity, and mark it as a quality indicator. That's it. The backend will generate 36 axioms, class and property declarations, domain and range axioms, and annotations. Most importantly, these new entities will preserve links to the core ontology via these hierarchical relationships and thus make the data described by such domain ontology processable by our generic machine learning pipeline. To sum up, our ontology construction solution allows the users without ontology development expertise in code knowledge in domain ontologies that reflect the specificity of their manufacturing processes. By using templates, process experts can share domain knowledge and data scientists can add information related to quality prediction. Thus, they achieve shared understanding of the domain and a machine learning task. Once we have an ontology, the user can integrate the data by mapping the raw variable names to its terms. For that, we introduce a compact graphical user interface with browsing functionalities. The resulting mapping is used by the extract transform load module of our system to prepare the data for machine learning. Due to the existing relationships with the core ontology, the ETL module will infer machine learning feature groups for all columns in the data and further process it without manual intervention. Processing strategies are specified by our machine learning ontology. For each feature group, it defines corresponding pre-processing and feature engineering operations, as well as the newly engineered feature groups. For example, the raw variable total resistance from our dataset was annotated as a resistance operation curve. It is a time series feature. According to the machine learning ontology, available pre-processing algorithms for time series are segmentation, interpolation, and sorting. Feature engineering operations for time series include computing various statistics for them, maximum, minimum, mean values, etc. This will be the newly engineered features added to the pipeline. The machine learning module of our system in turn has generic algorithms with the behavior specified on the level of feature groups, and therefore we can pre-configure various machine learning pipelines. Next, I will show how such automated pre-configured workflow operates. We can represent the workflow as a set of consecutive layers. After the manual step of data annotation, we obtain the uniform domain terms for each column in the data. The machine learning pipeline will then infer the feature groups for them. After that, in the series of feature processing layers, the pipeline applies feature processing and feature engineering operations, adds new features, concatenates them, and finally runs the machine learning algorithm to train and test the model. This setting largely speeds up the development. The only manual steps left here are the construction of domain ontologies and the annotation of datasets, and we provide a tool support for these tasks. Next, I will present the results of the user study that evaluates this tool support. The user study comprised 2 experiments. In the first experiment, the users were asked to describe their manufacturing process by filling in the proposed templates. In the second experiment, the users mapped the variables in the raw data sources to the data type properties in the ontologies they created. Before the experiments, the participants rated their domain expertise, experience with semantic technologies, and with data mapping tools on a Likert scale. After each experiment, the users filled in user experience questionnaires. We had 2 user groups, domain experts and data scientists, and 2 welding processes, resistance spot welding and hot stacking, and finally we collected 25 result instances for experiment 1 and 19 instances for experiment 2. As the metric for the effectiveness of our approach, we use correctness. In the ontology construction experiment, correctness is defined as the percentage of correctly chosen templates for a given term, template correctness, the percentage of correct choices linking the dependencies between classes, choice correctness, and the percentage of fully correctly created classes for which correct template was chosen and all dependencies were correctly specified, final correctness. The average correctness for applying a template was 93%. For making choices in the dependencies, 92%, and final, 90%. These numbers demonstrate the usability and high error prevention potential of the system. On average, our users needed about 50 seconds to create a new term, which is quite fast. In experiment 2, correctness is defined as the percentage of correctly chosen classes, class correctness, and the percentage of correctly mapped data type properties, item correctness. Most users correctly mapped column names in the suggested data sets, achieving 100% correctness. The average time they spent for each term is about 50 seconds. We also measured satisfaction, and it was evaluated with the questionnaires after each experiment. The questions were inspired by the well-known system usability scale and grouped over 6 dimensions: user-friendliness, self-explainability, consistency, completeness, descriptive power, and communication easiness. The radar charts show that all 6 dimensions have average scores over 4 out of 5. This indicates a general very good impression of users. The scores for dimension 6, communication easiness, and dimension 5, descriptive power, are the highest. This supports our vision that ontology can serve as a good communication base. Dimensions more related to the system usability have scores around 4, which means there is an improvement space for the user interface. The comparison of scores given by the domain experts and data scientists reveals that the data scientists evaluate the system with higher scores in average and with smaller standard deviation. This indicates that the data scientists have better and more uniform opinions on the system than the domain expert users. One reason could be that the tasks for data scientists were only related to quality indicators and thus were more clearly defined, while the tasks for domain experts who described complicated manufacturing processes were more demanding. We also analyzed correlations between the self-reported expertise of our users and their performance. There is a strong negative correlation between domain expertise and time in both tasks. There is a positive correlation between the domain expertise and all types of correctness. It's not surprising, because the users with higher domain expertise provided more corrected modeling and mapping solutions and were faster than the beginners. The figure also shows insignificant correlation between the performance of users and their experience in semantic technologies and mapping tools. This result is encouraging since it suggests that the usage of our system does not require any prior experience with similar technologies. To conclude, in this work we presented a Bosch use case of automated welding and the challenges with machine learning-based quality monitoring. To address the challenges, we propose to enhance the machine learning pipeline development with semantic components for ontology construction, data annotation, and machine learning workflow automation. As can be seen from our user study, having learned the template technology, domain experts and data scientists were able to generalize the approach to other manufacturing processes. Our system is currently deployed in a Bosch evaluation environment, and we plan to further push it into the production. This requires testing with more Bosch users and in other use cases. This also requires to further improve the usability with more advanced services. Overall, we believe that ontology can develop into a standard way of knowledge organization in engineering and bridge engineering and data science. Thank you.